Welcome to AP Podcast 6.3. This is on Hess's Law, and we're going to continue on with our enthalpy journey. And we've got a new term here, and that is state function. And enthalpy is a state function. And what we mean by state function is that's how it got there. We don't really care about all the different paths. It's kind of like your bank account. All right? You've got some kind of total. Let's say you have $1,000 in your bank account. You don't care if you put in $50 a whole bunch of times or took out $2,000 and added $3,000 and all that kind of thing. All you care about is this last little bit, what it is right now. Well, the fact that enthalpy is a state function makes it pretty easy for us because all we have to really worry about is like an initial and a final value. We don't have to worry about that. In fact, some reactions take 5 or 6 steps to get to where they get to. We just are going to worry about the fact that the final answer is going to be based on whatever there was initially and what there was finally, and you can subtract the two. So that's a really important thing. And we mostly deal with state functions in this class. So let's look at a reaction right here. We've got some nitrogen gas and some oxygen gas, and we put them together and we make some NO2. Now notice this takes 68 kilojoules, all right? Endo or exo? Well, obviously you say that's an endothermic reaction. Somehow that takes energy. So this is not necessarily a favorable thing. But what happens in real life is this reaction occurs in 2 steps. It doesn't occur in just one, and your whole chemistry life, all we've ever done is wrote a reaction like this. But it really occurs in 2 steps. So because enthalpy is a state function, we could just add up all the steps and get this value right here. So that's important. So let me show you exactly what's going on. I've got a diagram over here. So here's the first reaction. We get some N2 and O2 come together, and what they make is they make 2 NOs, and that it turns out takes 180 kilojoules of energy. All right, so that takes 182 kilojoules of energy. Then some oxygen is added to the NO, and that releases 112 kilojoules of energy. And so again, what we have is N2 plus O2. It looks like to us 1 step in the previous reaction, but it's really 2 steps. Well, overall, what's the energy involved? Well, it takes 68 kilojoules to get that reaction to go. So that's kind of what we're looking at. And Hess's law is most students like it because once you get the hang of it, it's really easy. But we're just trying to figure out what's the total energy involved, and it completely depends upon how many steps and adding them together. There are a couple rules that we need to go over, so let me show you what I'm talking about. When you look at all the different reactions, and I'll show you, I've got an example here in just a second. When you look at the different reactions, there's only a couple things we could do to manipulate an equation to make it work. One, we could reverse a reaction. So here's our reaction. N2 plus O2 gives you 2NO. And that takes 180 kilojoules. Well, if we reverse that, if we were to take some NO, decompose it, and make some nitrogen and oxygen, that would give off 180 kilojoules. So if you have a reaction and you have to manipulate the equation somehow to get to the final equation, and you've got to flip one, well, it's simple because all you've got to do really is flip the sign. So that's one thing you do. Okay. Now let's say you've got to manipulate some equations to make them work out, and you've got to multiply the coefficients by some kind of integer. And usually it's going to be 2 or 3. It's going to be something small. So let's say, for example, that here's our reaction right here. NO, N2, N2. Well, look what happened here. What do we multiply all those coefficients by? And hopefully you're going, oh, we multiplied those by 3, right? Well, if we multiply those by 3, like we did right here, we would then have to multiply 180 by 3. And there you get 540 kilojoules. Now, maybe none of this is making sense, but I've got a practice problem I want you to try. Actually, I'm going to do it for you, and then I've got one for you to try, and just to see how it works. So let's look at this problem. Here's a practice problem. All right, so here's the problem. Look, this is really what they want us to do. They want us to calculate the change in enthalpy for the reaction. And when they're talking about the reaction, they're talking about this one right here. A couple carbons plus some hydrogen gas makes some C2H2, which is acetylene. And it turns out that this reaction actually takes place in 3 steps. So we've got over here, we've got step 1, we've got step 2, and we've got step 3. Okay. Now, again, enthalpy is a state function, so we don't really care about all these little steps. We just really want to focus on this. How do we manipulate those 3 equations to get to this final reaction? Well, let's look at the first reaction. Look at this. Okay. C2H2 is on the reactant side. But look over here. It's on the product side. So what do you think we should do? Well, if you're saying we should flip it, you're absolutely right. So let me try and write that out here, if I can squeeze it in here. So that gives us 2 CO2s plus H2O yields 5/2 O2 plus C2H2. Don't let the 5/2 bother you. You'll see it's going to all work out. Okay, now, the important thing, the super important thing is, okay, I flipped the reaction. What do I've got to do with this value right here? Well, hopefully you said I've got to get rid of that sign, right? So I've got to make it a positive 1,300 kilojoules. All right, so I've got that. Now let's look at my second reaction. Carbon, oxygen makes CO2. How does that relate to this final reaction? Well, look at this reaction. We've got 2 carbons. Okay. Over here we only have 1 carbon. Don't let that 2 bother you. That's just step 2. So what have I got to do this whole thing? I've got to multiply it by 2. How convenient. My 2 is right there. Okay. Now if I multiply that by 2, what do I got to do with this? Well, hopefully you're going, yeah, you got to multiply that by 2, right? So that gives us a negative 788 kilojoules. All right. Okay, and then let's look at our last one. H2 is on the products, or on the reactant side. It's on the reactant side. There's only 1 there. There's 1 there. I don't think we do anything with that. So now we've manipulated our equations. We've multiplied 1 by 2. We've gone ahead and what do we do the other one? Oh, we flipped it. So now what we have to do is we've got to make sure everything cancels to give us this. And if it does, then we did it right. So let's go ahead and look at what we have here. Let's see. I've got 2 CO2s right there, right? Notice there's no CO2s in that whole final reaction. So hopefully they cancel out. Well, let's see what I've got here. Oh, wait, you know what? I made a mistake. My 2 CO2s are over here, aren't they? I flipped that. And then look, I've got 2 CO2s right here. Remember, this 2 means 2 of those, right? So those cancel. That's a good thing, right? Because there's no carbon dioxide in the final product. So that works out well. Let's see, what is there any other compound that's involved in these intermediate reactions that don't show up? Well, hopefully you said, hey, there's some water there. Well, let's see. I've got 1 water over here on the reactant side. Any water here? Nope. Ooh, I've got 1 water over here on the product side. Now, I got a little lazy, guys, and I didn't write the state of matter. But that is important, okay? It's important that I should have put an L there because sometimes we get things changing state as part of the intermediate steps, and we've got to account for that. So anyways, we've got 1 on each. So the good news is those 2 cancel out, okay? So far, so good. All right. Now, look at this reaction. Do you see any oxygen in there at all? Well, the oxygens are going to have to cancel out, right? So hopefully they're going to cancel out. Well, let's see what we have. We have 5/2 O2. Now, I'm not a fan of halves, but we use them. Well, look at what's on this side right here. 1/2 O2. So that 1/2 O2 cancels, right? And it cancels 1 of those. So instead of 5/2, I have 4/2, right? And what's 4/2? 2, you said, right? Okay. And then look what I have here. Remember that 2 goes right there, right? So I have 2 O2s there, 2 O2s there, so they also cancel. So I'm feeling pretty good. This seems to be working out. Let's see what stuff is left. On this first reaction, well, there's some of that. On this second reaction, there's some of that. And on the third reaction, oh, there's some of that. And then when you put them together, do we get exactly what the problem required? Let's see. We have carbon, 2 carbons. we have one hydrogen, and we have one acetylene. So there you go. They all added up. Now the important part is what happened with the answer, because look what it says. Calculate the enthalpy for the whole thing. Well, all I got to do, again, because it's a state function, I'll just add them up. I've got 1,300. Remember, this is gone. I've got 1,300 plus a negative 788 plus a negative 286. And if my math is right, I get 226 kilojoules. So I did all that work to get this little bitty answer right here. And hopefully that made sense. And so there you have a Hess's Law problem. Now, we'll practice these in class because it takes a little while to get the hang of them, but once you get the hang of it, it's pretty straightforward. So, again, if you have questions, we'll go over them. See you next time.